Without further ado, let's jump in here. I always like to start by acknowledging the group, the various students and postdocs and alumni that have worked on these projects. My talk is going to cover basically several decades of work, maybe the last decade. So some of these guys have graduated, and also my collaborators at Cornell and at Waterloo. I'll say a little bit more about that, and my funding from NIH and from ONR, which made all this work possible over the years. It's been very generous. And but as in the intro was alluded, Moore's law we've had pretty good 50 years, starting in 1965, until when Moore sort of propounded his law. He didn't call it Moore's law; it was Kwabena that gave it that name. But this continued until about 2004, 2005. You were actually doubling the number of transistors on a chip every 2 years. And you were able to do that, increase the clock speed proportionately without increasing the amount of power that the chip was dissipating. So things were getting cheaper, and transistors were getting cheaper, and you were getting more compute out of it at the same time for the same cost. If you zoom into the last, 2004 or 2002 to 2017, you can see that this, basically what I was saying, this is how many transistors you can buy for $1. Okay, so back in 2002, it was 2 million, and it plateaued at about 20 million transistors per $1 10 years later. And at 28, something happened for the first time, 28 nanometer process going from 28 to 20, something happened for the first time in 50 years, which is the cost of a transistor went up. Okay. And Moore's law is not really a law. It was only happening because it made economic sense. You were getting cheaper transistors. But if transistors are getting more expensive, it doesn't make any sense. Okay?
Well, and so people don't give it enough credit to Newton's inverse square law.
Okay.
People who used to draw masks, it's basically how long it took for you to have a linear dimension, which is actually 3 years. But you get 4 devices instead of 1.
Okay.
I mean, it's really that simple. I mean, not enough people credit the inverse square law.
Okay, so that's basically where we are. And the question, there's, I don't think there's any simple answer, and it's really hard to really figure out why this happened. But I'll give you my theory, and I like to appeal to really, my bent is to actually think about what are the fundamental constraints that are constraining us at the physical level. And, how close are we getting to those constraints, and how is that dictating, some of these constraints and these problems. And so if you have a channel that's about 30 nanometers wide, that's basically showing you how many electrons you have in the channel of that transistor. It's not a lot. You really have something like 6 lanes of electron traffic.
That's the scale.
Yes, that's the scale. The width of a lane of traffic is about 5 nanometers. That's the distance at which if I start bringing 2 electrons together, the work they have to do equals kT, the thermal energy that they have, which means that the electron will stop in its tracks when it gets to within 5 nanometers of the other one. You can easily do this calculation. Now, the caveats here are basically what you assume for the permittivity of silicon, which will change that distance. But it may be a factor of 2. It's a question of whether you account for the silicon dioxide that's nearby, or you just use the silicon and so forth. And then there's charge screening and so on. But it's about 5 nanometers on average. And so in a 30 nanometer wide channel, this could be like in a 10 nanometer process, you would have about 6 lanes of traffic. And since I went to graduate school at Caltech and spent a lot of time driving on the freeways, I always, this is the 405 freeway in Los Angeles. It's got about 5 lanes of traffic, and that's basically what you have in a transistor at that scale. And what the challenge has been is to continue to shrink the footprint of the transistor so it occupies less space on the chip. So you can increase the number of transistors in the setting area of the chip. And now we are getting to like countable lanes of traffic. How do you do that without reducing the number of lanes of traffic that you have? Now at 28 to 20, and other fabs are transitioning, Intel went to the FinFET, where basically they adopted the solution on the 10 freeway where you have this like, you know, carpool lane that if you're lucky enough, you can get up there and you can zoom. And, but in this case, it's not a direct analogy. I'm out of juice on this. So in this case, you actually, now you have lanes going across the three sides of the transistor, or the FinFET as it's called. And you know, this actually allowed them to actually shrink the footprint without actually decreasing. They increased the number of lanes of electron traffic, okay? Because they used a pretty high aspect ratio. And so this tells you that was important to them. There's other reasons why they did this, but let's think about what happens as we continue to shrink transistors if we actually just stayed with a planar process and we reduce the number of lanes. And what you find is that, you know, it's not so nice as it is in LA. You know, the freeway is more like, in a transistor is more like this, you know, freeway in Boston. And, you know, the electron, when it's trying to get from the source to the drain, actually sees all these dopant ions that it sort of has to navigate around. And so at actually 28 and 20, they got rid of the dopants in the channel to make it nice and smooth like it is in Los Angeles. And so that's an intrinsic channel to get rid of this problem because that was blocking a bunch of lanes. You freed up all those lanes. But you know, you have another problem here, which is that accidents happen. You know, electrons that are traveling along those lanes can get trapped, and the current level will drop. This is in a 45 nanometer wide, 24 nanometer long device, actually measured data. And you can see almost a 40% modulation in the current, which means that this device it's actually intrinsic. This device had on the order of, you know, 2-3 lanes of traffic that were open. And so just blocking one when an electron got trapped and the other electrons has to route around it, that was a big change in the amount of current that was flowing. And so with this kind of stochastic behavior, you can imagine once you get down to a single lane of traffic, your ultimately scaled device, a trapping event will shut off your current completely. And the amount of time it takes for the electron to get enough energy thermally so that it escapes is exponentially distributed with some time constant that could be microseconds, milliseconds, and so forth. It depends on how deep that trap is, as they say. Okay, so these are sort of fundamental physical constraints that we have to deal with as we continue to shrink devices. Now, it turns out that our brains are actually working with ultimately scaled devices. These are called ion channels. They pass a single lane of ions. And it's dealing with this problem in spades, okay? So this is a nice, you know, molecular dynamic simulation of a bilipid layer. So that's the membrane of a neuron. One side of this is the inside of the cell. The other side is the outside of the cell. If the students can humor me, does anybody know what these little red with the little gray, two gray things and the red, big red thing is? What molecule is that? Exactly. Okay, so you're filled with water. And we have these green and cyan colored things are ions. Does anybody have any guess which ions they are? Sodium and potassium. Okay, very good. Now, any guesses which one is cyan and which one is green?
Green is sodium.
Exactly. Very good, very good. So then do you know which side is the inside and which side is the outside of the cell? These guys know a lot of biology. That's cool.
Higher concentration sodium inside.
Actually, it's outside. The way that you remember that is that we evolved in the sea, so we had seawater, salt all around us, so the outside of the cell has got sodium, and the inside has potassium, and it's the concentration gradients of these, you know, ions on either side. You know, the cells actively maintain the gradients by pumping them back to where they were supposed to be. That's like your p-n junction, and then that will drive current. You know, majority carrier current in the right direction just by diffusion. Okay, but basically all the physics and drift diffusion, all that stuff, it works beautifully, and there's beautiful, you know, mathematical descriptions of this process. But what I want to focus on here, as you can see, basically that these transmembrane proteins, it's a tetramer, there are 4 of them, and they form this sort of extra cell, this space here, and then a very narrow pore. This is Armstrong dimensions. This dimension is about 3 nanometers across. And those potassium ions are going single file through that channel. And we are dealing with, you know, people have actually been able to measure the current flow through a single ion channel. And it looks very much like the same random telegraph signal that you see in transistors as they get very, very narrow. In other words, the flow of current is about 5 picoamps, but it randomly shuts off to 0 and so forth. And you can also have the opposite depending on what voltage you have, if it's a voltage sensitive channel, because the conformation of the proteins can change and close the channel. But even in that case, you get occasionally randomly thermal energies enough to sort of change that to the open configuration. So, inside your brain, these single lane, basically, devices that you're using are opening and closing randomly all the time. The only thing that the neurons do is they control the probability or the duty cycle. They don't rely on it to be open or closed at any particular time. Okay? And you may think that, by averaging across tons of ion channels and so on and so forth, you can get this to work, but the energy budget is pretty tight. Okay? And so I'll say a little bit about that. But just to give you an idea, okay, let's skip that. We can get back to that if you want some questions. We have ground to cover. So how does the brain actually do computation, reliable computation with these kinds of stochastic devices? Okay, and it turns out that it's actually quite distinct from the kinds of computers we built before World War II, which were these analog computers, and what we built after World War II, and we've continued for the last 50 years or so. 50, 60 years. These are digital computers. And the distinction is in the way in which you need to make a distinction between the representation you use, signal representation you use for computation, as opposed to the signal representation you use for communication. Okay? So, before World War II, we're sitting in this quadrant here where we had analog signals for communication and analog we manipulated these analog signals. In this particular case, there are these electric motors driving shaft. It's a mechanical computer. The amount of rotations of that shaft is your variable or your signal, your operand. And then the gears that you engage and the ratio and so forth. And if you do a differential, like in your reaxle, you can do all kinds of neat things like integration and differentiation and all that with all this mechanical stuff. But then eventually you spit out a certain number of rotations. So it's analog representation for communication, and analog, basically analog means a physical analog. The mechanical system is directly trying to use the physical primitives to emulate the calculation you're trying to do. And then after World War II, we actually switched both, right? We use digital now representations to communicate or represent these operands, and we use digital logic to combine them to generate the results, right? Now the brain sits in this quadrant where it's using analog for computation because analog degrades more gracefully with noise. So when I have this kind of stochastic switching happening in my ion channels all the time, I can't rely on 0 or 1 and that kind of thing. So we're using analog. Everything that happens in the dendrites, I'll show you a little movie about actually all this going on in the dendrites and the axons and so forth and define those terms, is analog. That's how inputs are combined to generate an output. But analog is not good for communication. In other words, it's susceptible to noise and so forth. So the brain goes to a digital representation. These are these spikes to communicate its results. And in digital, we all know, communication is an identity operation. So by using error-correcting codes, the way we encode the information, we can correct for errors. So it doesn't matter if your cell phones are doing this all the time. There's a lot of bits you're losing when you're going through the wireless, when you have a poor wireless link. So in that case, it's pretty straightforward to correct for errors. So this combination is sort of really a distinct third quadrant, which we haven't really explored in a lot of depth as a way of doing computation. And I'm going to argue that that's really the key thing that distinguishes what the brain is doing or what the neuromorphic approach is from just a purely analog computer or a purely digital computer. And so this is a movie here. I give you a neurobiology 101. But given that people know what sodium and potassium and so forth, you probably don't need this, but it's cool. Do we have sound? Oh, you can hear it, yeah. Actually, okay. So that little, it's a spike propagating down the axon of a neuron. And those are ions coming in, current flowing in, and then current flowing out. So the voltage goes up and then it goes back down. That all happens in like a millisecond. These are just conducted by ion channels. And so that's how a neuron communicates their output to other neurons. And at the terminals of the axons, there are these things called synapses, where if the voltage rises, these vesicles will bind to the membrane and release their contents, which are these little red molecules. They are ligands And in this case, this ion channel is ligand gated. So when it binds, it opens. And that's how then these ions here then flow across into the input side of the other cell, which is the dendrite. And whereas these pulses that you saw traveling around are 400 millivolts, that's the voltage supply in your brain, 1 millisecond wide pulses, once it hits the synapse, it gets converted to some graded potential, which people like to think about as the strength of the synapse, but actually that graded potential has very little limited dynamic range. It's microvolts to millivolts. And so that's now, those low microvolt, millivolt scale signals are then combined, tens of thousands of them within the dendritic tree of a neuron. It hits a certain threshold at the cell body, a spike gets emitted, and then that's how you communicate that result, okay? So that's really why I'm saying that computation is analog and communication is digital in the brain. And so just to summarize, so on the axon end here, we have digital communication. One thing to note here is that there's actually, when a spike invades the axon terminal, 2/3 of the time, nothing happens. It's that unreliable. 1/3 of the time, you see what happened in the movie where the transmitter gets released, it binds, and you get the signal on the other side. So this probabilistic kind of behavior is happening even at the level of a total synapse. Now, then on the dendrite side, you're back to a sort of an analog signal. You combine them in an analog fashion. Now, if you actually run the numbers, which will take, it's very easy back of the envelope calculation. How many neurons do you have? How many synapses are there? How many synapses do you activate per second? It turns out that it's on the order of, because how on average how fast the neurons fire. It turns out that the brain is activating on the order of 10 to the 15 synapses per second. Okay, I'm ignoring the 2/3 that actually fail, okay, but I'm just saying this is the rate at which spikes are invading axon terminals per second. And if you look at the total amount of energy the brain uses is 20 watts, okay? So the overall energy at the system level to activate each synapse, including all the energy it takes to conduct the signal along the axon, distribute it over there, and then sum it all back and convert back to spikes per synapse that's activated, it's 20 femtojoules. Now, to put that in context, if you take an ion channel, you open it for 10 milliseconds, and it passes an average of 1 picoamp, okay, across 100 millivolts, that's 1 femtojoule. So this number corresponds to just activating on average 20 ion channels per basic primitive operation, activating a synapse at the system level, including all the wiring and so forth. So it's not like you're doing this by activating a ton of ion channels and averaging all this stochasticity out. Does that make sense? Okay, the energy budget is pretty tight. Okay, now, because these 20 ion channels actually can't all be in the synapse. Some of them are also being opened along the axons and dendrites and so forth. Okay, so how does the brain do this? And this is what these neuromorphic engineers, or neuromorph for short, are trying to figure out. In fact, this guy is salivating looking at this very beautiful neuron, and he's trying to build a copy of that. Yeah, that's what the economists think we look like in our labs. But but the point is, we don't want to slavishly copy. We want to really understand the principles, and at the highest level is this combination of analog and digital. And we want to see then translate those principles into working hardware, or basically find a way to compute with the ultimately scaled transistors, which will be down to a single lane of electrons, and we'll be switching stochastically just like an ion channel, completely on, completely off. And so the way that I've mapped out how to do this is what I call, I'm borrowing this from Elon Musk, the Neuromorphs Five-Point secret master plan, okay? So this is the route to world domination, okay? And it's a 5-point plan. And the first 2 points I've already made and go back to, the mid-'80s when Kwabena started exploring this whole area and he coined the term neuromorphic, was to actually implement dendritic computation with subthreshold analog circuits. This is how you can get down to the femtowatt, picowatt level, energy levels that are comparable to what you're seeing in the brain, using basically very small currents. And then implement axonal communication with asynchronous digital logic. You don't want a clock, because once you start getting those variable delays, because sometimes the transistors are going to shut off randomly and so forth, you want a system that can wait until the signal is actually acknowledged, and then it moves on. And so we can be tolerant to this sort of robust to this intermittent setup, which will just prolong the delay. And then you want to then scale your pool-to-pool communication. I should actually switch this, but I have a pool of neurons that are computing something. I want to then communicate that to the next pool of neurons. I'm using, like in the brain, all these axons carrying all these signals. I want to do that in a way that scales linearly with the number of neurons that I have. Otherwise, my brain is going to explode. If it's quadratic, I'm going to just have all wires in there. Okay, and this is something that's you can actually look. If you look at the brain closely, you can figure out some ways, the ways it does that, and you can emulate those. I'll talk about those. And then you, of course, to make the thing robust to, defective neurons or failures, intermittent failures and things like that, the computation has to be performed not by a single neuron in any instance. It should be distributed, performed in a distributed fashion so that the computations itself. And so these two go together. Once you distribute the communication, then you have to do a lot of communication. And so you need to sort of get both of this to scale linearly, and we need to have a way to map that computation on there. I'll talk about how we do that. And then this last part here, this is 0.5. We've already accomplished these four. 0.5, we are just starting to look at that now. There's been some theories developed that show us that this is possible based on these kinds of looking, modeling, adding another level of sophistication to the way that we are modeling what the brain is doing at an abstract level. But basically, last thing is to encode continuous signals and spike trains with precision that scales linearly with the number of neurons. Right now, it scales like the square root of the number of neurons or the total spike rate, which is not so great. But if you're able to accomplish all five, and we think we have a way to do five now, so we're on the verge of dominating analog and digital with this neuromorphic approach, which I'm going to summarize in this slide. This is the world domination part. The way that you do that is, I think people are familiar with this curve here. This is showing the energy per operation. And this is showing the precision of that operation. So in a digital system, if I'm in like an 8-bit system, I have 256 levels. And so my precision will be somewhere around here, around 200. In an analog system, I'm just looking at my signal relative to my noise amplitude. And so, like if my noise is 1 millivolt and I have a 100 millivolt signal, that's a precision of 100, okay? And so that's the precision. And it's well known in digital that, I can it costs me logarithmic cost to get precision, right? Because I add a bit, it doubles my dynamic range, it doubles my precision, okay? And so you're on this logarithmic curve, but you start out really high because you're using these logical primitives that are very primitive, like zeros and ones, ons and ands and ors, inversion, inverters. And by the time you compute something like a multiply accumulate, at 1 bit you won't do it, but it costs, probably full adder is like 30 transistors and so forth. And so if you take into account all the transistors you're switching, and the fact that I'm doing this calculation for a certain continuous signal, that, like I'm doing a DSP type thing where I've got some continuous signal and I'm trying to low pass filter it. And so I also have to take into account, do very small steps that are some multiple of the frequency, okay, to do my Euler step and update. So for these kind of continuous input, continuous output, anything in the real world that's taking out sensory signal and doing some action like a self-driving car is dealing with continuous in, continuous out. And so I'm focused on those kinds of applications. If you take into account all those factors, you find out that your overhead is pretty high. Okay, but then once you pay that overhead, you add one more bit, you double. So it just goes up logarithmically. And as technology, this is what Moore's law did for us. As technology was progressing and transistors were getting smaller, the capacitance you're driving, the voltage is getting smaller, all that. The energy per cost individual switching event was going down. So like this is real data based on measurements from 90 nanometer, and this curve is measured from 28 nanometers, which is, I couldn't get 14 or anything more recent. It's all simulation data. But this is for multiple accumulated. So it's sort of calibrated. And so I'm comparing that with traditional analog computation. Now, in analog, my noise is kT. kT is the energy, right? I can convert that to voltage, and which will be, the energy is like the voltage squared. And so for me to get a signal to noise ratio of 1, my energy would be kT. My signal has to be the same as the noise, okay? But then as I increase my precision, like if my voltage is 100 millivolts, my noise is 1 millivolt, right, my energy is quadratic in the voltage, right? So to double my precision, I'm going to go from 100 to 200, but my energy is going to go up 4 times, okay? So traditional analog, circuits and everything, have this quadratic increase in energy with precision. Now, we basically have figured out a way by combining analog with digital in this sort of neuromorphic fashion to get, precision to scale linearly, or energy to scale linearly with energy. Okay, if we're able to do that, that's a 5-point master plan. If you execute all those 5 points, you'll be on this curve, and you'll basically be able to achieve the lowest sort of energy per operation across something like a five orders of magnitude, 5 to 6 orders of magnitude. Okay, and that's what I mean by world domination. Okay, so I'll tell you how far we've come and how I think we're going to do the final step. Okay, that's what this talk is about, and I already made that point. Okay. And like I said, I'm not going to spend time on this. In the 80s to the 90s, and the 90s to the people did a lot of this kind of stuff. From the mid 90s to mid 200, people did a lot of the, communication of spikes and building up that infrastructure. And we're finally able to just about, 5-6 years ago, build million neuron systems with billions of synapses on them, based on all that work. And scaling this thing up to the million neuron, billion synapse level required us to do a good job here where we can communicate efficiently from one pool of neurons to the other. So I'll talk about that next, okay? And this is based on actually emulating the way that the brain wires up its axons and dendrites. So if you look at a pool of neurons here, talking to another pool of neurons here, such that they are fully connected, you never see this in the brain. You never see an axon go in here and go and hit the cell body of another cell, right? And neurons have what are called dendrites. Okay, this is key, right? Because what happens is it eliminates these terminal branches, right? So you can basically just come here and basically synapse. So there's very short branches here, but you're synapsing into these 3 guys. And yes, you replace this wiring with that wiring. Okay, but there's a difference. Does anybody see why this is better? Having the wiring on this side is better than having it on that side.
Well, you're going to end up with 3 on every one, so it doesn't matter which one of the 3 is alive and which one of the 2s are dead.
Okay. But there's actually, that's true. It looks like, okay, it doesn't matter, but there's a distinct difference here between this dendrite and the axon. In other words, this dendrite, this axon has made a synapse and it's delivered a signal to this dendrite, okay? But at this point here, I'm combining these 3 signals into one dendrite. So this guy is carrying the 3 signals from these 3 guys. And I can do that recursively. I can continue to merge. This is we do the map operation and then we do the reduce. We are doing the reduce recursively, right? We're not transmitting all those things all the way to where they need to go. As they meet, they combine. And so I'm reducing. That's what a dendrite is doing, right? And so this, because a dendrite can carry multiple signals, whereas an axon is just carrying the same signal from that one neuron, this is more efficient. Okay, the diagram doesn't show it very well, but you can exploit that.
You assume linear propagation?
That's a very good question. The way we've implemented it now, we are assuming linear. The dendrites are linear, which is not really the case in real biology, but we don't know how to exploit that yet. So our sort of compiler can exploit the linear. I'll explain that. We separate the nonlinear part, which happens in the thresholding to go to spikes, from the linear part. So the dendrite part is linear in this case. And so in that case, you can even go further, right? Because the linear system, I can use one, tree. I explain here. We can actually use a resistive network like this, right? And we can basically now, let me just go back to this case. So if we try to emulate this in silicon, what we do is we don't have all that massive wiring, so we actually multiplex. So if any of these neuron spikes, we send its address, and then we have a decoder that will recreate the spike at the corresponding location. Okay, so to implement this fan out of 3, we have to send out 3 addresses of these 3 targets. And then they'll get hit ping, ping, ping sequentially. Okay, but now if I emulate the dendrite, I can actually just send one spike into this network. And now I have a dendritic tree where you can see with the color, this guy will get a strong input, but it will decay by the time it gets to here and so forth. And so now each neuron, but then this is a linear system, so I only need one resistive network, right? And each guy just taps. And the relative location between the input and output to determine the weight simultaneously. So I can do this really efficiently, okay? If it's nonlinear, it's a little bit more expensive. You can't actually do this. But this works very nicely, and I can get more into why, once we get to implementing computations, I can explain more why. But that's the first thing we did to really cut down. So now instead of, we basically cut down the amount of traffic we need by a factor equal to the number of neurons in that pool that we're trying to hit, okay? And so then the next level, you can do this again at the next level up. So now if this pool is not just talking to this pool, but he's talking to 3 different pools, then the question is, I'm just see how I'm doing with time. Then how do you, again, can you do this kind of thing? Now we are working on the axon side of things, right? Again, you never see this in biology. You never see a cell sprout 4 primary axons, okay? No, what it does is that it will basically send, it will replace these 2 long guys by 1 long guy, and it will make 2 short branches next to the targets. So this is minimizing wiring, okay? It's like the flip side, okay? And so what this is saying is that the way we emulate this in hardware is that instead of building a flat organization here, we use a router that's organized like a tree and can implement multicast. So instead of sending these 4 guys where each one is targeting one of these 4 pools, we send one and it replicates as it goes through this tree-like routing network. Okay, this is something you can't do in a mesh because you deadlock if you multicast, but you can do it in a tree. Okay, and so with those 2, so again we gain cut down by a factor of 4. So we actually have a factor of 12 total. Okay. Which is great, which actually makes your traffic scale linearly rather than quadratically. It doesn't, you factor out the other n, which is the number of pools and the fan out. And so this is sort of what the architecture looks like on Neurogrid. We're actually tiling the neurons in a 2D array. And we implemented a 2D resistive network. It's a hexagonal grid. And this is actually done with transistors. We have an elegant way of doing that with transistors.
What about inhibition? Isn't there a topological?
Oh, you can do inhibition just fine because inhibition will sort of pull current out. So if you go back here, if you go back here, right, I can dump current in or I can pull current out, right? So inhibiting is just pulling current out and exciting is pushing current in. That's what happens in the dendrites, okay? So it's not did I answer that or no, you don't, it seems like I got that wrong.
I'm just wondering how linear it really is.
Oh, okay, yeah. I mean, it's linear if you're injecting current in and you're pulling current out. It's not linear if you're doing conductance-based synapses where you're modulating, like the strength of this conductance to ground or another conductance to, okay. So it depends on how you actually use it. We've done both. When we want to be very biological, we've implemented the conductance-based thing, but when we're actually just trying to use it to do some computation, we implement the stuff where we can compute, we can synthesize the right solution with. And so just pointing out the architecture. So we actually have these neurons tiled in 2D across the chip, and then we have the single, transistor-based resistive mesh. And so, for example, if this neuron spikes here, its address will be communicated up the tree. And here at this RAM, we can translate that address into as many targets as we want to hit. But these are just the centers, okay, which correspond to these guys lighting up. And then the neighboring neurons around there will receive with some decaying profile a corresponding weighting of that, which means that neighboring neurons will have similar response properties. And so you want to organize your computation in such a way that you tile your neurons in that way, okay? But this is what we're doing. And then actually we can also multicast. So we can route down to we can choose any subtree. And once we hit the parent of that subtree, we just replicate going down that subtree. Okay. So using these techniques, we implemented this. I have one of these boards here. I started working on this project, like a year after I got to Stanford. And I got here at the end of 2005. And so in 2006, and we basically, between 2006 and 2011, we developed basically the hardware. And it took another couple of years to build a whole stack on top of it so that you can write Python code describing what your network you're trying to implement is. I'll show you a little bit of that GUI, and you can visualize, interact with real time. Okay. And, so we're in 180 nanometer. We have this mixed analog digital approach. And IBM started this project, the Synapse project, where they built True North. And actually, the guys who designed Neurogrid are the same guys who designed True North. 5 of my students now work at Almaden in that group. But IBM was conservative and they went with a full digital approach. But this gives us a nice control. Okay, what are we getting from the analog part? Okay, this is also a custom design to actually do neuromorphic computing. And so basically, at the level of number of neurons, they are in 28 nanometers. They're able to fit 16 million neurons on a chip, whereas we have, a million neurons on a chip. So with 16 chips, they have 16 million. We have 64K neurons on a chip, and we have a million on this board here. And but we are able, because of these techniques we are doing with the hierarchical routing and the dendrites, we're actually able to connect each neuron to something like 8,000 others. So we can implement like 8 billion synaptic connections. In True North, each neuron can only connect to 256 other neurons. And they are routing constraints. So here, the largest system they've implemented has something like 4 billion neurons connecting those 16 million neurons. And the power dissipation of this 16-chip board versus that 16-chip board is about 3 watts versus 7 watts. And so if you compute, given the rate at which we're activating synapses in these two cases, it works out to be about the same amount of energy per synaptic operation, about 45, even though this process is 40 times more dense. Okay, if you take into account the voltage scaling and the size scaling, if this was implemented in the same technology as we are, there would be 20 times more. It would be 20 times more energy. So another way of saying that is that we are 20 times more efficient, given the with the mixed analog digital approach. We just taped out basically 2 weeks ago. We just taped out a chip in 28. It's still mixed analog digital, and so you just have to stay tuned and see what those numbers are. But and it's also doing something completely different, which is this. I'll talk more about. Okay, but Neurogrid was really designed to basically model, biophysically detailed, with different kinds of ion channels, like Hodgkin-Huxley type networks with multiple compartments, all this stuff. It was funded by NIH. But so now that's what's allowed us to get to sort of million neuron, billion synapse networks. It was basically the first million neuron neuromorphic system was Neurogrid. And now we are saying, okay, now we reach this scale. It sounds pretty interesting. We should be able to do some interesting computation with this, okay? Now, and so this is the part I'm going to talk about next. How do you sort of map computations onto these neuromorphic chips, okay? It turns out that there's actually been quite a bit of work done in this area, but just to sort of, relate it to, more familiar territory, back in 1984, when Xilinx was making gates with about 9,000 gates on them, FPGAs with 9,000 gates on them, people were going in and twiddling these bits in the logic blocks and twiddling the bits in the switch blocks. You basically had to be a chip designer to use one of these FPGA chips. Now, you can get a chip with 4 million gates on it, and nobody goes and even knows that there's these things like lookup tables in there and switch matrix. You just write your VHDL code. You say multiply this by this, and then do all this kind of stuff, and it all automatically synthesizes this logic for you, okay? Now, this is the problem we're trying to work on. We're trying to basically come up with the equivalent of VHDL for neuromorphic chips. In other words, nobody wants to go and say, oh, the weight of this synapse should be this, and you should connect this neuron to that neuron and all that stuff. That's how we're doing it how people were doing it before we started this project 3 years ago. Now, that's basically a very limited number of people. Maybe you need a PhD in neuroscience to really figure out how to do that stuff. But, if somebody has some algorithm or has some dynamical system, like a Kalman filter or some control system they've already implemented, we want to be able to just take that functional level description, these equations, and just map them automatically. We have a synthesis tool that will just take care of everything, and the chip will just do it. Okay, and so that's sort of I think this is sort of the next big challenge in neuromorphic engineering, and so we started this project back in 2013. It's a collaboration between us, the University of Waterloo, Chris Eliasman's group, Rajat Manohar, who's an expert in asynchronous VLSI design, and he's sort of responsible for the routers. It's founded by ONR from Shagan Bata as the program manager. And the goal was to build the first neuromorphic chip designed to perform arbitrary computations with networks of spiking neurons. And write Neuromorph, this is a synthesis tool that will automatically configure Brainstorm to perform the desired computations. And this is based on theory developed by Chris Smith. But before I get into that, I'm just saying this is how you visualize what's going on. Basically, the Waterloo group already has something called NANGO. I'm using it in my class that I'm teaching this quarter on neuromorphics. And it stands for Neural Engineering Objects. And it's basically a really nice GUI, or you can write Python scripts with just math or some dynamical system you're trying to implement, and it will just synthesize your spiking neural network for you. But it will run that, it will simulate that on your processor, right? And so we are designing Brainstorm to sort of be the backend for Nango, so it would actually then run it on the real neuromorphic chip, okay? And so they've got a very nice front end, very easy to use, very intuitive. And so that's sort of the Nango, the front end of us. We're keeping that front end of the system. And then we are developing this synthesis tool that will then, it's like your VHDL compiler that will take that network description. Basically Nango will take it from the math, the functional level, to sort of the network description, the weights and the connectivity. And then we'll take that. We have to do some optimization. There's certain things a little bit different. And we'll take that and then we'll basically map it onto the bit pattern that goes to program the chip. And so you have something like this. You have your application specifications. In Nango, you generate an NEF network description, and then Neuromorph will then map that onto your chip, and you deploy your chip in whatever your embedded application is you're interested in. And so this is intro to how we do this. How do you map computations onto networks of spiking neurons? Say you wanted to compute the norm of a vector. Okay, you basically square x, square y, add the two, take the square root, right? But this is not how you do it in an FPGA, right? In an FPGA, you go with more like a data flow type of implementation where you build a squaring unit, you build an adder, you build a square root unit, and the information will just flow through, okay? Now, in a neuromorphic chip, we do the same thing. Instead of having gates and wiring between them, basically each of these operations will be performed by a pool of neurons, okay? And this pool here will basically encode the input X in its pattern of firing. Like each neuron will fire at some rate. And so I'll have a set of 5 rates that represent X, and as X changes, these different rates will change, okay? And then basically the computation that you want to do, like squaring, I have a way of computing decoders which are weighted combinations of these rates such that A becomes X squared. It sounds like magic, but it's like machine learning 101. It's very straightforward, right? So with these different, I'm just coloring them now so I can show you how each neuron's output rate depends on X, okay? And that's like this. So as I sweep X, the purple neuron doesn't fire, and at some point, value of X starts firing, and then it saturates. Okay, the blue neuron, he starts firing a little bit later. The yellow neuron goes the other direction. I forgot to point this out. We actually randomly assign these encoders, which are +1 or -1. So some neurons like X to decrease, some neurons like X to increase. And so that's why this guy got -1, he's going there. The rest of the variability is just inherent in the neuron itself. It has got some random threshold, it's got some random gain. And when we fabricate these things in analog, we get that for free, okay? It just comes with the chip. so there you are. And so that's what those tuning curves look like. Okay, they're called tuning curves, and these are the fine rates, okay? And so the problem you want to solve now is you want to find some weighted combination of this curve, that curve, that curve, that curve, such that when you scale them by those weights and add everything together, you get X squared, okay? And this is a least squared problem you can solve, machine learning 101. Okay, so that's what we do. We measure these curves. I'll get into what we do a little bit more specifically, but basically that whole approach can be extended. Like you basically don't have to do the whole data flow, modular approach. You can actually build one network to do the whole thing in one step. In this case, you basically build a pool, which we call a 2-dimensional pool. It represents a 2-dimensional variable. And you do that by assigning each of these vectors some random vector from the unit sphere, okay? And so you take the inner product of that vector and this, and you get a scalar, which is the current that's going to be input to this neuron. It's going to fire at some rate. And you solve the same least squared problem so that you get this thing in one shot out of the population, okay? Now, this book came out in 2003, more than a decade ago, where Elias Smith and Anderson sort of laid out this whole thing. It's called the Neural Engineering Framework. And they've actually, this is the Nango. This is just showing you the thing in action. So in this case, I have, there's a pool of 49 neurons, 7 by 7 array here. They have different thresholds and different gains, as shown here. And I'm feeding them some input that's varying sinusoidally. And that generates this pattern of firing. And if I look at the individual membrane potentials of each of those neurons, they're going up, hitting a threshold, reset, going down, hitting a threshold again. And then if I basically just plot the spikes, each one is emitting, I get that. Now, if I take these spikes and I put them through a low-pass filter, which is what the synapse does, when a spike hits the synapse, it opens for a certain amount of time, it decays exponentially afterwards. I can convert these spikes into continuous signals. And if I solve my least squared problems, it'll tell me how much to scale each of these. This is an estimate of the rate, if you want to think of it that way, of each neuron, a continuous time estimate of the rate. And if I then do my least squares problem, I can find out how much I need to scale each of these traces. And it turns out that for the black guy, I should scale him only a little, and for the cyan guy, I should scale them a lot. And for this red guy, I should put it a negative weight, scaled a little bit. And if I take those scalings and I add them back together, I get my sinusoid. Okay, so this pool of neurons has done the identity operation. It's encoded the X in a distributed pattern of firing, and we can decode back X out. That's just the identity. You don't need to do that, right? With the same technique, you can just solve to approximate whatever you want, function of X, okay? So that's shown here. So in general, I have some pool of neurons, and their pattern of firing is representing some quantity X. I solve for these decoders, and I get back some multidimensional function of X, f of X. In the case I showed you, we solve for identity. And then I can take those decoded, we call these decoder quantities, and I can encode them in another pool of neurons. Okay, so this is what happens in NEF, from pool to pool to pool. And so you can do several steps of operation and so forth. Now, of course, everything that happens, the decoding, these are just adders. They're just summing these weighted things together. And the encoding is just taking this vector and inner producting it with that vector, the encoding vector. Everything is linear here, so you can actually collapse all that down into one matrix. And this looks more like your conventional neural network, right? Where this weight here is the inner product of this decoder and that encoder, okay? And so it's like the neural networks that you're familiar with, except that we have a low rank. In this case, the rank of this matrix will be 2. Okay, so you can represent it in a much more compact form by storing encoders and decoders, which we really like when it comes to hardware. It's much cheaper. It's not quadratic, it's linear in the end, okay? And so, but you can also do more than that. You can do dynamic transformations. So this is showing you how you can implement a controlled integrator. Okay, so you're basically saying X dot is now a function of X itself and the input. Okay, so this alpha here is actually an input. So you have a set of neurons. Because X depends on X, there's a recurrent connection among that pool. This control is the alpha. And there's an input coming in as well. So the control is controlled by this. The input is controlled by that slider. They are plotted up here and down there. And if I run this, you see that's the activity of the neurons. This is X, which is what the solution to this nonlinear dynamical system. And this is the input. So I gave it a little kick input. It integrated it as it's supposed to do. I gave it a kick down. It integrated that. And then here, A has gone back to 0. So I've disconnected that, and I can make it unstable by making A very large, and I'm losing track of which one is. But this was all, you give it this dynamical system, and it generates the network that does this. Okay, so this is basically a nice synthesis methodology for building networks. In this particular case, because the dynamical system, this is a little bit technical, so if you don't get this part, it's okay. I just want to give you the flavor. It's like a whole book. Okay, I'm trying to summarize here. But if you know anything about linear systems and signal processing and all this stuff, you just take some time, and it's very straightforward. But just to give you the flavor, this is how you actually implement. I showed you an NEF network where I had some decoded quantity, and then I was encoding in another pool of neurons. But in this case, for a dynamic transformation, or so implement some dynamical system, these same neurons project back to themselves. Okay, so I can take that thing and I can decode something out of it, right? And also, it's important that the synapses are not just multiplying by weight; they're actually filtering. Okay, so each spike triggers an impulse response. That's a decaying exponential. So it's a first order low pass filter. So you can exploit this dynamics to implement your dynamical system, okay? And just real quick, so the system I was trying to implement is x dot is some nonlinear function of x plus some input. Okay, if I multiply this by tau, I get the tau x dot, and I get the tau c, and I add x, I get tau fx plus x is equal to this g of x right here. Now, the interesting thing about this is that if my decay of my synapse, my time course of my synapse is tau, then this is saying that to implement this dynamical system, I should drive a low-pass filter with g of x, defined as follows, and my input scaled by tau. So what all I have to do is to take this population and decode from a g of x, defined as that, and feed it through the synapses, and I've implemented this dynamical system. Okay? And it works. Okay, that's what I showed you. And so they've actually used this approach, it's called the neuroengineering framework, to build the world's first whole brain model. Okay, so this is a model which has like 4 million neurons. And each one has like 30,000 synaptic connections if you don't factor it into the low rank representation. And it's basically got a retina. That information feeds into visual cortex. It goes through sort of the frontal cortex, which is doing sort of cognitive type operations, short-term memory, things like that. And then its output, when you present it information, it thinks about it and it writes down its answer through an arm. So there's a motor cortex that's controlling the arm. It's the full loop, sensory, cognitive, motor. And all these operations were implemented within the same framework, which is the only, NEF is the only thing that can do that. If you're trying to learn these things, you use reinforcement learning for motor stuff. You use back propagation for your visual thing, and then in the middle of the cognitive stuff, nobody knows how to do that. Okay, with the learning rule. Okay, so at this point, if we want to do all these things within the same framework, this is the state of the art. And here I'm going to play back this video. So in this case, in Spawn, it's called Spawn. It can do up to like 9 different cognitive tasks. Some of them are on the level of like intelligence, IQ test questions. And so I'm just going to play one of these tasks, an example of one of these tasks, and it's told on the screen which task it is, and it autonomously, decides how to handle that information after. Oh, sorry. Okay, I'm not getting that.
The fifth task is a question-answering task.
This is
Spawn is shown a list of numbers and is then asked a question about the list. There are K questions and P questions. Here it is asked a P question, which means it must indicate what is in the position number provided. Here it's asked what is in position 5. This task demonstrates that Spawn has flexible, rapid access to information that it encodes.
Okay, so this is all pure spiky neural network synthesized with NEF from end to end. Okay. And so the question is, so the next question is, does this work in like real chips, real hardware, and like this kind of analog stuff, okay? And, I wouldn't be giving this talk if it didn't. So like if I take one of the neurons on Neurogrid and I measure the, what we call response, I just inject current into each neuron. And the same, basically, and the neurons are designed identically, but because of mismatch in the process and the fact that I'm operating subthreshold where I'm exponentially sensitive to this mismatch, I have a huge degree of variability. Like if there was no mismatch, it should start firing at 0.5. But some neurons start firing at 0.2, and some neurons don't fire until I hit about 0.85. And they also have slightly different gains, like this guy is steeper than that. So this is just a sample of 100 neurons giving you an idea of how much variability we have in the process. And the question is, can we, these are physical primitives, right? I go and measure them from the chip. It's like a physical primitive. Instead of my ands and ors, I have these are my primitives for computation. And so the question is, can I use NEF to actually map computation onto these physical primitives? And so, yeah, so once I measure these tuning curves, I go and I do the same thing. I do least squares optimization across these tuning curves, compute decoders, and then I feed that back into the chip to weight the fine rays appropriately. And so I'm going to show you an example where we did this with, like 1,000 neurons on Neurogrid for vector rotation. So we encoded a 2-dimensional vector in the pool of 1,000 silicon neurons on Neurogrid. We implemented, instead of decoding back XY, we decoded XY times this rotation matrix. And, as you see there. And so this is showing you the data. I'll pause this for a second. Okay, so it looks pretty, but it's like real data from a chip. Okay, so let it go. 1 second. Okay, good. Oh, shit, sorry. Okay, but what you, well, okay, I'll explain with this. Then what you're looking at is the input, and we are using this color wheel to represent the direction of the vector, okay? And each neuron has an encoding vector that's chosen from the unit circle, so we can also paint the neurons themselves with different colors, okay? And so what you see here, when the colors are not saturated, it's saying that those neurons are not responding strongly, but if they start responding strongly, the color will get more saturated. And since we assign these encoding vectors, after the fact, we program them in, we basically choose to organize this wheel as a cylinder. So like basically the preferred direction sort of rotates. All these guys have the same preferred direction. Like these guys are sort of blue in this direction. These guys are sort of orange in the other direction. And it goes through the full 360 as you go left to right across the chip. And so if I present a vector that's rotating like this, you see the activity move along because the neuron which has that direction will be the one that's responding the closest. But I can also change the amplitude. So what I do is I present, so I'm plotting in XY space the vector that I'm presenting. And then here I'm just decoding that vector back out. So here I build decoders for identity. So I should just get the same thing I saw here. Then here I'm actually connecting these guys by decoding this minus 60-degree rotation and then encoding it. And so these guys here should be then always be 60 degrees behind, but the same amplitude, okay? So just watch for that when it runs. Okay, so you can see, hopefully when it ends, it will stop there. You see what's happening? You can see how this guy lags, but he follows the amplitude. See that? And so that's the rotation happening. This guy's just identity, so he's always on top of it. And this is the input that I'm putting in. Okay. And so this is like 1,000 neurons on Neurogrid doing this. And these are some individual spike trains from the 2 pools of neurons. And we've gone beyond that. We've actually collaborated with Osama Khatib, whose lab is on the first floor. And we implemented his operational space control in a neuromorphic chip. So basically, he provides the control, relies on basically how do you get the end effector of a robot to apply a setting force. Okay, so what you need to do is you need to take those 3 force components, and you need to take the current joint angles of the robot, and you need to then do sort of this Jacobian and all this stuff, which is dependent on the current state of the angles. And then that will output, your 3 torques that you apply at the different joints, okay? And so, for example, like this torque is composed, we basically decomposed the problem because we had the math. We could look at which terms, collect terms that depended on the same things. And so we were able to decompose this torque into like a term that depended on these 1, 2, 3 things. And another term that depended on these different combinations. And so then we have to sum those 5 terms, 1, 2, 3, 4 terms to get the right torque. And just to give you an idea of the complexity, for example, from this pool, we are decoding minus 0.35 sine Q0, which is this angle, the rotation on the base, times the cos of Q2, which is this up-down angle, times the x component of the force. That's what we have to compute. And then there's 3 other terms like this that gives you the first torque, and the rest follow. And so just showing how accurately we can sort of decode this expression from this pool of 256 neurons. The dots are what we got out once we solve for decoders and we apply them. And the surface is sort of the correct math that we're trying to do. And then we can actually go put it on the robot. It's able to control to a position of about 2 centimeters in a 100 centimeter by 100 centimeter workspace. I'm just going to show you a video. This is Stanford PR. They got some nice shots there. And how am I doing for time? 5:30. Yeah. We're going to 5:45. Okay. And this is a 8-chip version of Neurogrid. We implement the weights on the FPGA. But, so the user interacts with the robot in this sort of virtual 3D environment. That's just a CAD rendering of the robot that's animated with the current joint angles. He's moving this green ball around, and that then determines the vector between the tip and the ball as the end effector force we generate. We feed that to Neurogrid along with the 3 joint angles. These are the 5 pools of neurons. Those are their spike trains. And you can see it tracks the green ball pretty well. And this is just, he's pushing on it here. And this is Samir Menon, led this project. He's pushing on it here to demonstrate that we've got a force control, right? So as you push, it just pushes back with whatever force we're trying to generate, the controller is trying to generate. So, and like I said, this is sort of the kind of GUI we have for Neurogrid, and you can basically interact with it in real time. And so I'm pretty much done. I'm going to summarize with sort of the step 5, which is the last thing. I've showed you how we can basically build large-scale systems by following these sort of hierarchical wiring patterns, dendrites, and axons in the brain. I've showed you how we can map arbitrary computations onto pools of spiking neurons. Using this sort of neuroengineering framework, we can also do dynamics as well, dynamical transformations, any nonlinear dynamical system as well. And then the last part is sort of this part about how efficiently can we do this? Like basically, what does it cost us in terms of precision? I told you that traditional analog scaling is quadratic, and we like to be on a linear scale. And so I'm going to explain how we get on that linear scaling of precision with linear scaling of energy with precision. That's all I have left, right? That last part. This is just telling you, this was actually neat because we didn't originally design Neurogrid to do NEF. That's a new chip we just taped out in 28. It's supposed to do that. But we implemented this up on Neurogrid, so we had to sort of implement a way to do the weighting. And the way we did it is, Neurogrid already has a daughter board, which is the RAM that's sitting at the top of the tree, and where you can do arbitrary, kind of connectivity. And so basically in that RAM, we, instead of just storing, like when a spike happens, and this arbiter sends the address out of that chip and it goes all the way up to the tree, to the RAM. Instead of just storing the addresses of the targets we wanted to route that spike to, that's this address, we want to send it to 0. We also store a weight. Okay, and what we do is we just generate a random number. And if the random number is less than the weight, then we let the spike through and it hits that neuron 0, okay? In the case where the guy spikes and the random number is bigger than the weight, we just drop the spike, okay? So all the stuff I showed you with the controlling the robot and doing the vector rotation, all the stuff was happening. We're dropping spikes on the floor all the time. Just to demonstrate that the stochasticity I showed you at the beginning, this kind of computation is immune to that, okay? And which is what we are looking for. So we don't yet have transistors that are small enough that we're getting that kind of probability thing, but we'd love to have those and to exploit that, okay? And so, I'm not sure why it's repeating. We did this already. Okay, so we covered these, I sort of skipped these, and we covered these 2 points, and this is the last 10 minutes or so. I'm going to give you a quick story here. It's not a very long story because I'm just telling you, I'm going to tease you how we can do this. We're actively working on this. And so in the case, the way we are doing things now with NEF, let's say we have some step change in some signal. We apply that signal to these 5 neurons. Because of their different variability, they spike at different rates. And I've just organized them so the most excitable guys first. And then we take these spikes, and we pass them through, we weight them, and we put them through a low-pass filter synapse. And that's our estimate of what actually happened, what the input was, okay? This is our decode. And you can see here, because of spurious coincidences, like in this case, it just happened that all 5 spikes lined up, we got a huge fluctuation, okay? And so if we allow the neurons to spike independently, then when we sum these spikes together, they look like a Poisson process, okay? Not exactly, because we know, the fact that somebody is going at this frequency guarantees we won't see any interval shorter than this. But when you go to large numbers of neurons, the Poisson approximation is pretty good. And so from that, it tells you that you're going to get fluctuations or variance here in your decode that's equal to your mean. Okay, and that's just how the Poisson statistics works. And it's just like electrons in a wire, short noise in a current. Okay, in any interval of time, you count the electrons, you get 100, then your variance is also going to be 100. And if you take the square root of the variance, you get 10, so your precision is 100 over 10. That's your standard deviation, your mean over your standard deviation, and so your precision is 10. If you want to double that, you have to go to 400 electrons in that time interval. Okay, then your square root will be 20. And then you get 5% precision instead of 10%, okay? The same thing has happened here because we are allowing the spikes to fall whenever they want. And so by doing things like this, we get sort of the same analog scaling that you have. Now, Back in 2013, Sophie Deneb published a way of doing this such that you get linear scaling in your precision with the number of neurons or the total spike rate. But you could only do it for a linear dynamical system. And just last year, Rahul Mamasheimer published a paper showing how you could extend this to a nonlinear dynamical system, implement any arbitrary nonlinear dynamical systems. And it's very interesting. Their solution looks like this. I sort of nicknamed it coordinated spiking. Okay. Where basically what is happening is that it's the flip. These neurons look like they're spiking randomly. Individual neurons look Poisson. But when you superimpose decode, you get something that's very irregular. Okay, so it's as if the spikes are slotting in to slots. Basically, for you to minimize your fluctuations, you want to have very regular spikes coming in. So you go up a little bit, you correct, you go up a little bit, and you just keep that, going on. But now, and as you increase your number of spikes, you just linearly squeeze down this noise. Okay, and so the way they do this is basically by okay. So let me say. So this gives you sort of the coordinated spiking gives you a linear scaling of precision with your spike rate. And this independent spiking, which is what we're using now, gives you a square root scaling. And for example, in the controlling the robot joint case, if I wanted to have, basically 1% accuracy, I can drop, if I do this, I only need 2,000 or 3,000 spikes per second. If I do that, I need about 500,000 spikes per second if I want to have 10 millisecond response time. Okay? Basically, 10 milliseconds is the window over which I'm counting spikes. You can think about it that way.
What is the speed of generating random numbers?
Oh, yeah, in that case, well, we have a linear LFSR, linear feedback shift register on the FPGA on the daughter board. That's how we're doing it right now.
How is that tied in? How is that related to the spike rate?
Oh, it's just the same. Each time a spike comes in, you shift the thing and you get a new number. So it's the same as the rate, yeah. But this is we have other ways of doing this now in this new chip, which are much more efficient. But stay tuned. Okay, yeah. But this has been published. How we do it in Neurogrid has been published. You can read about that. Any other questions? Okay. So this is really a big win if you're able to do this. And it's a bit complicated, but all you have to take, you guys already saw networks that look like this, where we have a pool of neurons and we have it recurrently connected. Okay. And the way in which these coordinated spiking neurons work is you have the regular synapses we have that are filtering to estimate the rate, but they have fast inhibition between the neurons. So when the neuron spikes, it updates the other neurons on its state. And essentially what you're doing is you're feeding back the error. And after you spike to correct the error, it goes away and the other neurons don't spike to correct the same error. And then the way that you basically able to do a nonlinear, or the way that, if you like, you program computation onto these kinds of coordinated spiking networks is that you train what's called an echo state machine. Okay, it's a recurrent neural network where the individual units are continuous rate units, but they have like a tanh transfer function. And so you find a set of weights, this A matrix, X is your vector, the variables you're dealing with, your vector quantity. You find a set of weights A that can approximate whatever dynamics you want, given this tanh nonlinearity in each of the units. And once you have that, basically, these guys provide a recipe to then transform that into a spiking neural network, which will approximate those dynamics, but we'll do it in such a way that the precision scales linearly with the number of neurons or the total spike rate in the network. Okay, so we're actively looking at implementing this in silicon right now, but they actually have simulations and papers probably showing that it actually works. So that was the last part, the 0.5 of the master plan. And this is just to remind me that if X is two-dimensional, then you have these two quantities that you're encoding and decoding back into. And so let me just summarize by saying we are on the cusp of realizing the full promise of combining analog computation with digital communication as the brain does. These hierarchical organizing principles made it possible to scale communication rate linearly with pool size. This is how we were able to build Neurogrid with millions of neurons, a million neurons and billions of synaptic connections. The neuroengineering framework makes it possible to perform arbitrary computations with heterogeneous physical computational primitives. These are all the mismatch among the neurons and so forth. It's not a problem. But precision scaled with the square root of the pool size or the total spike rate. And these coordinated spiking neurons networks offer linear scaling of precision with pool size. And if we hit that linear scaling, then we are going to basically dominate analog, purely analog or purely digital processes, computational methods over like 6 orders of magnitude of precision. Now, you can read more about this in detail in this paper that just came out. There's a special issue about the ends of Moore's law that was put out by this Computing in Science and Engineering magazine. It's written for a general technical audience. And so you can basically get the, dig in all the material I've covered. Yeah, it's on my site. You can just go to Brains and Silicon. And you can get a look under journal publications. And for the students, I'm teaching neuromorphics. We're going to cover all this stuff. You can just come. You don't need a lot of prereqs, just 102, 102A. And so those of you who are interested in learning this stuff for the students, you can just join my course this quarter. Thank you very much. Right on time.
Yeah, perfect.
Question?
Yes.
So, screwdrivers and hammers are both good tools, but they're good for different things.
Absolutely.
So, listening, I have some ideas about maybe where this is going to be the best tool, but I don't really understand it. So I want to ask you,
Yeah,
where you think this is going to be the best?
I think this is complementary to your conventional computers. It's not going to balance your checkbook. It's going to, you don't want to add some random 0 in the 10th decimal place or random 1 when you're balancing the checkbook. So when you need precision, like I said, digital is always going to win at high precision, okay? But there's this intermediate range of precisions, not too low, not too high, where the most energy efficient approach will be this approach. And so you're looking for applications in that domain, okay? And I'll give you some examples, but that's the important thing. That's the deep message. So we've got a lot of things, self-driving car, getting a robot to come into this room and sit down and navigate around, where 64 bits is not the reason why we can't solve the problem. Right, these are a whole set of problems. We're dealing with a lot of data. None of it is particularly important. And we want to do some action. It doesn't have to be super precise. It just has to be the right one. And so these kinds of things, especially in the domain where you're taking continuous real-time information that's changing over time, and you're doing something continuous real-time action, and you're closing the loop so you have a chance to correct because you can see what you did, you can account for it. It don't require a ton of precision. They need everything to be rapid real-time. But this is why I focus on continuous signals and dynamical system. Not only time has to be critical. There's a lot of redundancy from one frame of a video to another. You shouldn't treat each one as some random image like you do right now when you put it to a deep convolutional network. You can get rid of all that redundancy if you have something that understands time and is keeping some state and is feeding back. So this whole set, but that tends out to be the problems we have right now. These are the problems that are exploding. Okay, everything you make autonomous has to deal with this kind of problem, some sensory, some cognitive, some motor, closing the loop, embedded applications. I think that's where this technology, these kinds of solutions are targeted for. So keep your bank account safe on your digital machine. But yeah, question.
It's only going to be continuous functions. What is the equivalent of settling time that you would have in a digital circuit? There has to be something.
Yeah, exactly. So this is also why it's important to have your you see, so when, this is actually a perfect question, right? When I change the input to some of my neuromorphics, or even I change the input coming into your retina, it's going to take some time for those neurons to respond. And it's probably going to be another 15 milliseconds before they're going to forget what they saw and be fully responding. That's the settling time. Hang on a second, that's the settling time, right?
That means the whole thing is a low pass.
Yeah, that's true, but this is why you have to design a dynamical system, because if you design a dynamical system, then you're inherently accounting for. You see, when I write down, when I write down, when you write down your, and I haven't done this, when this is why you want to, give the system, describe the system you're trying to implement in this form, okay? I've left out the tau here, like if X, this is a nonlinear system, but you can imagine that this thing has some speed at which it responds. And the speed at which it responds is different from the tau at which the synapses respond. The fact that I can still have that tau and approximate any dynamical system means that any speed you want, I have a way of implementing it. But you have to explicitly, this is why you describe, because this is saying there's some settling time. It's a dynamical system that you're trying to implement.
Not when you're emulating this in an FPGA, but if you're going directly to a physical process.
Yes, this is what I'm doing.
What determines tau?
What determines tau is this time constant of my low-pass filter. So when a spike hits a neuron, I have an impulse response. I've designed a low-pass filter, and that's a tau. It's programmable.
Okay.
And then I need to know that tau, and if I know that tau, I can basically map whatever dynamics you want, and I can rescale that tau.
So
either use
a fundamental constraint in the same way that power is a fundamental constraint in ordinary circuits?
But you have to distinct power from precision. Right? If you're limited by, if you're bending a certain amount, if you want to get a certain precision, you have to bend a certain amount of power. That's independent of how fast you want to go. Because that's just your shot noise or your KT over C noise that you have in your system, right? And so I'm saying
my field, I don't know.
So I'm saying that those individual circuits, I can be operating with very very high noise in my individual circuits. But by distributing across the population, I can get higher precision at that level, right? So I'm distinguishing. I'm sort of, instead of trying to get all the precision from this random flow of electrons. I'm not calling for a lot of precision at the individual circuit level, but because I can control spikes precisely, I can do better overall than I would if I just let the electrons do their thing, right? Yeah. But that's so high level explanation. Those are all very good questions. And a lot of this stuff is active research, and people are figuring out new stuff every day, and so it's very exciting ideas here. Some very new and exciting ways of looking.
Extremely dumb question.
Yes.
The board that you have, that's entirely comprised of normal silicon substrate, right? There's nothing.
Yeah. These chips are implemented in a 180 nanometer process. I think we use in this case we use an IBM process, and custom design, of course. But yeah, that's
And you mentioned that.
And the new chip we put out is a standard. It's in a 28 nanometer.
And you mentioned a Python library that people can download. Sort of play with.
So this is Nango. So this is hosted by the.
Build the brain, the same.
Exactly. Yeah. You can just download it. It's open source stuff. You can start playing with it. You can give some.
And so will this be compatible?
Exactly. So this not this chip, but Brainstorm, which is a new chip that we are designing. The smaller version of the test chip is called Braindrop, which we just taped out. Will then be the back end. When you sit in Nango and you just say, we have something called Nango Brainstorm that will just synthesize it to the chip.
So to play with that, I had to go to your course. Right?
Pardon me?
To play with that, I had to attend the course.
Oh, but you can download it yourself. There's tutorials. You can download Nango.
No,
to the chip itself.
Yeah.
Yeah, the chip is not back yet, right? So maybe next year.
Okay.
It's going to be back in July. Yeah. Yeah. Okay. I mean, doing it on Neurogrid is a lot tougher because it wasn't designed to do that. So the students can't play with that. It's not so straightforward, yeah. Cool. But now we really have designed the software and the hardware together to work together.
Another question is, we have the GPUs leading the way for whatever they
Absolutely.
do. Mm-hmm. Where does this fit in that whole ecosystem?
Again, yeah. So when it comes to dynamics and time, GPUs not so great, right?
Yeah.
And also, there's also your power budget. Like if you're trying to, if you're in a car and you have a 10 kilowatt alternator, and you can put 1,000 or a couple of hundred watts into your GPU, that's fine. But if I'm a little drone that's trying to deliver something, I don't know that I can put my GPU in there. So I'm saying in these applications where you are more power constrained, I think this is where this approach will come into play. I think in the car, NVIDIA is going to own that. but maybe in the tiny autonomous drones, you start seeing this kind of stuff. And it's also a question of how much you want to do.
So are there some applications that you're right now looking which look really aligned to where this is?
No, actually, we're just starting to think about that. I showed you some robotics applications which we've done, and we've also done brain-machine interface. Like we've taken Krishna Shenoy's decoding algorithms for figuring out what movement some paralyzed person is thinking about in his motor cortex and automatically generating that movement. And we've been able to map those algorithms onto these neuromorphic chips as well as control the robot arm so we can do the full thing. And so those are some places we thought about, but I'm not, I think, this is some place we should think about some more actively
So
what we could do with
like
this kind of stuff.
5 to 10 years out before it becomes mainstream.
I think so.
Yeah.
Yeah. It's not going to eat your lunch anytime soon.
Okay, thank you.
Okay.